So here's a table of values of the function f of x equals sine 1 over x. F of 1, which is really sine of 1, it's like 0.8. F of 0.1, which is really sine of 1 over 0.1, sine of 10, like negative 0.5. F of 0.01, which is really sine of 100, is also about negative 0.5. F of 0.001, which is like sine of 1,000, well, that's 0.8 and some more. Right? So the question is, are these numbers really getting close to anything in particular? Can you really say that if you evaluate f at values which are close to but not equal to 0, that the outputs are actually getting close to anything in particular? I mean, this is positive, negative, negative, positive, negative, positive, negative. It's looking pretty bad. Instead of a table, let's look at a graph. Here I've got a graph of the function f of x equals sine 1 over x. And you see the middle of this graph is just that horrible green blob, right? It's really hard to make out any detail. You might think that that's just a consequence of the fact that I'm drawing this graph with such thick lines, and if I used thinner lines to draw my graph, maybe I could, get rid of this green blob and really see some detail. But even if I dial down the size of the lines that I'm using to draw this graph, the blob thing is still there, And it's really there in the graph of the function. Even if these lines were true lines, 0 thickness, it wouldn't be possible to fit even a single atom next to the y-axis without touching the graph of this function. The graph is oscillating wildly near 0. Even if your input is very close to 0, your output could be anything between -1 and 1. So in light of this evidence, the limit of sine 1 over x as x approaches 0 does not exist, which sometimes I'll abbreviate DNE for does not exist. What does it even mean to say it doesn't exist? Remember the definition of limit. To say the limit equals something means that I can make the output as close as I want to L by making x close to A. So when I say this limit doesn't exist, I mean it's not the case that this limit is equal to anything. Right? If you tell me this limit is some positive number, well look, when I evaluate the function at a number very close to 0, the output's negative. So the limit's probably not some positive number, but there's also inputs very close to 0 that give positive outputs. So the limit's probably not a negative number either. And the limit's probably not 0 either, because none of these numbers are getting close to 0. So in this sense, this limit just doesn't exist, because it's not the case that this limit is equal to anything in particular. If you tell me this limit's equal to L, I'm going to show you numbers close to 0 which aren't close to L. Let's see another example along these same lines. Here's a particularly confusing example. Consider the function f of x equals sine pi over x. This function evaluated at 1 is 0. And that's pretty clear, because that is sine of pi. And sine of pi is 0. What about the function at 0.1? I'm claiming that's also equal to 0. The function at 0.01, that's also 0. This can be kind of confusing. I mean, take a look. Here I've typed in sine pi divided by 0.01 onto my calculator. This is calculating the function's value at 0.01. If I ask my calculator to do this, it is not telling me the answer is 0, right? The calculator is giving me this, admittedly a very small number, right? E negative 11 here, but it's still not actually 0. So can I convince you that this is even true, that the function's value at 0.01 actually is equal to 0? What is f of 0.01? Well, it's the same as sine of pi divided by 0.01. Now here I'm taking pi and I'm dividing it by 0.01. That's the same thing as what? That's the same thing as multiplying by 100. I'm dividing by 100th. That's the same as multiplying by 100. So this function at 0.01 is sine of 100 pi. What's sine of 100 pi? Well, think back to what the graph of sine looks like. Here's a graph of sine, 0 to 2 pi. If I do it again, here it is at 4 pi, and I do it again, here it is at 6 pi, and I'm going to keep on going, and eventually I'm going to get to 100 pi. And at that point, sine really is going to be equal to 0. Calculators are great, but they're also terrible. This calculator can't really calculate with pi. All it can do is calculate with some approximation to pi. We can use our human mind to evaluate this function exactly. In light of this evidence, you might be tricked into believing that the limit of f of x as x approaches 0 is equal to 0. After all of these points are approaching 0, and the function evaluated at each of these points is 0. So maybe that means that this is true. So it looks like the limit is equal to 0, but what happens if I look at some other points? Well, take a look at this example. Here's the same function, f of x equals sine of pi over x. This function, if I evaluate it at 0.75, is this maybe a little bit mysterious number, negative 0.866 and so forth. If I evaluate this function at 0.075, I get the same thing. If I evaluate the function at 0.0075, I get the same thing. At 0.00075, I get the same thing. 0.00075, I get the same thing. So what's going on here? Well, what is this number? I mean, 0.8666, this isn't just some sort of random number, right? This is, in fact, negative the square root of 3 over 2. And it looks like this function at all of these points has the same value, negative the square root of 3 over 2. So does that mean that the limit as x approaches 0 of f of x is equal to negative the square root of 3 over 2? I mean, again, all of these values, 0.75, 0.075, 0.0075, these input values are approaching 0, and the function's value at all of those inputs is the same. So what gives? Is the limit 0? Is it negative 0.8? Which is it? Okay, I've been a little bit too tricky in picking my input points. So here's the same function, f of x equals sine pi over x. And here, I'm picking a collection of points that's again approaching 0, 0.7, 0.07, 0.007, 0.0007. It's getting closer and closer to 0. But now, my output values are looking pretty random. I mean, they're not all the same, for instance. So this is maybe some evidence that the limit of sine pi over x as x approaches 0 doesn't exist. Here I've got a bunch of input points that are getting closer and closer to 0, but my output values at least don't appear to be getting close to. We're not just learning, we're exploring. I encourage you to cook up your own examples. We've seen a couple examples now of where limits don't exist, but can you come up with more?